Welcome all to this session. Thank you so much for your time. We are in module 3, where we're talking about the wireless LAN MAC layer. And in this module, this is the third session, where we're going to talk about carrier sense and medium access, of how at layer 2, the devices, the wireless LAN stations and access points can successfully access the medium, sense the medium, and talk to each other without any major issues. So before we jump into today's session, let us just quickly recap what we discussed in the last session. So in the last session, we were talking about mostly MAC framing, headers, and the key functions of the headers. We started with the base .11 frame format. We explained what is the base .11 frame. We said it's going to have a header and then a frame body, which is basically the IP payload, and it will have a FCS or a error checking mechanism at the end. And then we went into the details of what's the header, what's inside the header. We actually broke it down into multiple subfields. We said that a .11 MAC header has many subfields like the frame control. We talked about types, subtype fields, which distinguish the different types of .11 frames we see: management frames, data frames, control frames, and so on. We talked about the 2DS from DS bits and what they mean. We talked about the address fields, that there are 4 address fields, and we talked about sequence control, fragment controls, and things like that. And then we also went into more detail about the frame control field, and we talked about the various flags inside that, and explained all the functions of these flags and the types of type fields and so on. And then we went into the beacon frame in more detail. We explained what's inside the beacon frame. We said that beacon frame is one of the main frames that you would see in the .11 protocol, that is really advertising the capabilities of an access point, and it will tell you everything about the AP, right? And the beacon field has fixed parameters and also tagged parameters. We went into detail about what are the fixed parameters. We talked about the beacon timestamp, basically the beacon interval, the SSID fields and BSSID fields, and supported rates, extended supported rates. All the extra information elements we have when we had HT, VHT, EHT, and so on, HE information fields, and so on. And then we explained all those things in detail. And then we went through the other management frames. So we looked at the frame formats of probe frames, authentication, association, deauth, disassociation frames, and so on. We explained what's inside the frame body. We talked about reason codes and why a client would dissociate or disconnect with an access point. We talked about RTS, CTS frames, duration fields, what they do, and what is their significance. And then we went into data frames, talked about the data frame payload. We talked about what acknowledgement frames are and what is their significance, what are the contents of the frame body of the acknowledgement, and so on. So we covered a lot of ground in last session regarding the frame formats and so on. If anyone who missed that session, the recording should be up on the website on the course page. You should be able to go watch the recording and also download the slides from that session. Okay, so today's session I'm quite excited about. This is in many ways the core of Wi-Fi technology when it comes to the protocol part. So those who are really interested in Wi-Fi protocols and have been studying Wi-Fi protocols for a long time, this is something that we all learn when we are studying Wi-Fi, right? So we are trying to solve this basic problem of how do multiple devices access the medium and operate without by being good citizens and without not colliding with each other. That's really the multiple access problem. As I mentioned before, I'll go back to the same example. Let's say we have only one transmitter and only one receiver, and the transmitter is sending information to the receiver. Then there is really no problem. There is no one else here. The transmitter is sending information to the receiver. Our entire module 2 about wireless LAN physical layer was about that. How can a single transmitter successfully send information over a medium, over this medium, in this case it's a wireless medium, to the receiver without any issues? And how can the receiver receive that information over this medium in various conditions, multipath conditions, low signal to noise ratio conditions, noise conditions, all kinds of conditions? And how will the receiver receive the information? That was the problem that we were talking about in the past. Now, as we said, that is not how the real world works. The problem is much more than that. Now you have many such devices that are trying to connect to this access point, and they're all trying to have information, and they want to send information at the same time over what we call as a shared medium. So let's say I have one client here talking to an access point. Let's say there are 10 clients around this access point, and they're all within the reach of this access point, within the range of this access point. So that is what we call as a shared medium. So there is a medium between the transmitter and the receiver, but that medium is shared by multiple transmitters and multiple receivers, and which puts them in what we call as a common contention domain or a collision domain, where all of these are contending for the same medium. Remember that even though there are multiple transmitters and multiple receivers, there is only one medium, right? And only one person can access the medium at any given time. So that is what you mean by shared medium. Even though there are many transmitters and receivers, the medium is shared, so which means that only one person can transmit at any given time. And we need to design some protocol where this medium can be shared, but without having issues and conflicts and collisions. Just like if you take the example of a runway in an airport, there is probably one runway in the airport, and there are multiple flights that are trying to use the runway. Of course, we need to make sure that there is only one flight going on the runway at any given time, right? And how do you schedule that, and how do you make sure that there's only one flight on the runway at any given time so that there are no collisions, is really the protocol that we are trying to talk about here. And that is one of the most important things that we'll talk about, and most of today's session is about that. Okay, so now let us come to how multiple access works in various technologies. If you take a traditional technology like cellular networks, most of the cellular technology uses different multiple access methods. One of them being like let's take the example of TDMA, or a time division multiple access, where there is a base station, the base station tower, and the base station is saying, okay, I have 10 devices connected to me, right? So I am going to, as soon as my phone or my device connects to the base station will allocate a time slot to that particular device to communicate. So for example, I am communicating in one frequency band. Within that frequency band, you can actually, in the time domain, break it down into multiple time slots. And you can say, device 1, you transmit in this time slot. Device 2, you transmit in this time slot. Device 3, you transmit in this time slot. And the time slots are pre-allocated to all the devices connected in the cell. And when the time slots are pre-allocated, the problem becomes very simple, because I know when I need to transmit and I know when I need to not transmit, right? Because there are fixed time slots allocated to me. So that problem becomes fairly straightforward, and that works really well for cellular networks, because most of the initial cellular protocols were designed for voice traffic. And the nature of voice traffic is it is very deterministic, and it is not it doesn't need a lot of throughput. So if you're making a voice call on your phone, you are speaking, and then there are constant bitrate codecs that would take the voice that is coming out of my mouth and basically digitize it, and it will make it into like 20 frames per second or 30 frames per second. So within 1 second, there are 20 frames, 30 frames of voice frames, and it's a constant bitrate traffic. So when you have constant bitrate traffic where there is regular frames at regular intervals, the constant time slot based medium access is very convenient, because you have constant bitrate traffic, you have constant number of time slots available, and it makes the communication very deterministic, and it works quite well. But in the data world, where protocols like Ethernet and Wi-Fi have been designed for data communication, the idea is that data is not very deterministic. The data transmissions is not very deterministic. And so they ended up following this mechanism called CSMA, or what we refer to as carrier sense multiple access. So here we are saying, if there are multiple transmitters trying to transmit, let's take the example of this picture on the screen. There are 4 devices, device 1, 2, 3, 4, and they are sharing this common link. And this is the case of Ethernet, for example, right? So they're all sensing the medium. So what does carrier sense mean? This is the carrier, like the runway for your airplane, and you're sensing to actually see if there is any energy on that link. And if there is no energy, then you can access the medium, right? And so that's what's called carrier sense multiple access. In order for you to have multiple access, you're sensing the carrier, right? And so it's called carrier sense multiple access. And Ethernet, which is a wired technology where the information is transmitted over Ethernet cables, uses a technology called CSMA CD, or it's also called CSMA CD. CD stands for collision detection. So in this example, what happens is device 1 and device 2 both have packets to transmit. So device 1 starts transmitting, but they first sense the medium. The check of the medium is because it is, remember, it's still carrier sense. So you have to first sense the medium before you transmit, because you don't have deterministic time slots like cellular networks. So you don't know when you can transmit, when you're allowed to transmit. So first you have to check to see the medium is available. Only then you can start transmitting. So what will you do? You will check if the medium is available, and both D1 and D2 are checking, they're sensing the medium, and they both see the medium is available at the same time, and they both start transmitting at the same time. And when they both transmit at the same time, there is a collision. So in the case of Ethernet, what happens is, because the collision will generate some energy, and the energy is easy to propagate over a cable, and it is more deterministic to be able to hear that energy over the wire, in the case of Ethernet. So they use this method called collision detection. So that means that whenever there is a collision, there is a very high probability that all the devices will be able to hear that collision, because it's happening on the wire, right? And so as soon as you detect the collision, then the devices will say, okay, we lost the transmission, so let us back off, and then let us retry again. So they use the Backoff algorithm, they use the Backoff mechanism, and then they retry. So what is the Backoff mechanism and all of that? We'll explain that in the coming slides. Wi-Fi, on the other hand, does not rely on being able to detect collision, because there is a good chance that when a transmitter is transmitting to receiver over the air, and if there is a collision somewhere in the air, there is a good chance that that energy might not be able to be detected by the transmitter receiver. So you might not be able to detect a collision very easily over a wireless medium, right? So in order to address that problem, Wi-Fi uses a concept of collision avoidance. So what it is trying to do is, it is trying to avoid a potential collision, which means that some of the things that we are doing in Ethernet, like Backoff and things like that, are done ahead of time, even before you transmit. So to increase your probability of not having a collision on the medium. So how we do that and how the Backoff works and all of that, we'll discuss that in the next few slides. For now, I want you to only remember that there are two methods that are used in the Ethernet and Wi-Fi world for multiple access. It's called CSMA, carrier sense multiple access. Ethernet uses collision detection mechanism, and Wi-Fi uses collision avoidance. Right? How does collision avoidance work? We'll talk about that in the coming slide. So now let us start with explain some of these concepts that we just discussed using a very simple example. My favorite example, the example of a classroom. And here you can see there is Mr. Smith, who is the teacher, and there are students, Amy, Bob, Chris, and Dora. These are your 4 students in the classroom, and this is basically a classroom. So this is the representative of a Wi-Fi access point, Mr. Smith being the access point, and the students, Amy, Bob, Chris, and Dora being the clients, and then the classroom being your wireless LAN cell. So if you take that simple example, now since we are not using scheduled access, all 4 students might actually sense the medium, because they all have information to send. Amy has 3 packets to send, Bob has 3 packets to send, Chris has 3 packets to send, Mr. Smith also has packets to send. He has information to send, right? So let's say they're all wanting to send information, right, at the same time, and they're all sensing the medium. They all saw the medium, and right now the medium is free. So then they start transmitting. So all 4 of them transmit packets, and then there is a collision, right? So this is something that you want to avoid. You want to avoid this collision, right? And this is the classic multiple access problem. So how do you do this? How do you avoid this problem? Is what we are trying to discuss. So one method is the method that I was talking about, cellular networks using this method, right? Where you actually use scheduling, you allocate time slots. And this method is actually even tried in Wi-Fi as well. I'll explain that. There's something called as a contention-free period access, and where the access point, in this case Mr. Smith, can create a schedule. He can say, oh, here is the timetable. At time 0, Mr. Smith, I'm going to send 1 packet, and then at time 1, Amy can send a packet. At time 2, Bob can send. Time 3, Chris, and time 4, Dora can send information. And this timetable is broadcast or already informed to all these people, right? So they all know that this is the order in which they need to transmit. So this is what's called a scheduling. So, and then Mr. Smith does this scheduling. So this is what happens in the cellular world also, as I was mentioned before. So this is one method in which you can avoid collision. So when you use this method, then of course Mr. Smith will send first, then Amy will go next, then Bob will go next, then Chris will go next, and then Dora will go next, and they've all successfully transmitted a packet. They're all happy. there are no collisions, and they've all accessed the medium successfully, one after the other. So this is one method, right? Unfortunately, this method, fortunately or unfortunately, this method is actually not used in Wi-Fi that well, and there are a number of reasons for that. This method is called the point coordination function, where AP is doing the scheduling. So in this case, what happens here is, if you look at this picture here, there is something called as a contention free period. So which means that there is a period of time where there is no contention, and the AP or the access point is taking over the medium. So the access point is saying, all you clients, you need to listen to me now. I am going to take over, right? And I am going to control the medium, right? So how am I going to control the medium? I'm going to send out a beacon. In the beacon, I'm going to say, for this amount of time, like for the next 10 seconds, for example, everyone has to back off and just listen to me. No one can transmit until I tell you to transmit, because I am taking over the medium, right? And so that the AP can do that in a contention free period. And then as a part of the contention free period, the AP will send a contention free poll message to a particular station. So the AP will say, okay, you, Mr. Bob, you can transmit now, and sends a poll message to that station. And then that station will send a response, basically send one of its frames. And then again, the AP can now acknowledge that frame and then poll another station. And then that station will send its data, and then the AP will acknowledge that frame, and then it will poll another station. And so one at a time, it can send poll messages to each station, and then it will receive the data, right? And when the AP needs to transmit, it can just transmit. So that way it is avoiding collisions. This method has been in many ways deprecated. It's not really used in Wi-Fi, and Wi-Fi uses mostly this concept of what we call as the contention free or contention based protocol, basically where everyone contends for the medium. There is no scheduling, right? So let us look at how that protocol works. And that protocol is called, or that mechanism is called, what we refer to as distributed coordination function, which means that the coordination is actually distributed. So the coordination is not done by a point. So this AP is a point, right? If it is done by this point, it's called point coordination function. But if the coordination is distributed by everyone, meaning there is not one person doing the coordination, there is a distributed coordination, they're all coordinating with each other, then it's called distributed coordination function. So this is the method that's actually used predominantly in Wi-Fi. So to explain this concept, let me just take as the same example of Mr. Smith's class, right, where we have these 5 students, and to avoid collision. So this is the collision avoidance protocol. So if you're doing collision detection, all you have to do is all of them have to sense the medium, and if they all see the medium free, anyone can transmit, and if there is a collision, then they can back off and do that, right? But we want to have a collision avoidance mechanism. So how do you avoid collision even before you transmit? So first thing you do is all 5 people who are in this group would actually pick a random number between, let's say, between 0 and 5, right? So we are, all of us are asked to pick a random number between 0 and 5. So luckily, in this particular example, all 5 of them picked different random numbers. Now that does not happen every time. There could be multiple people picking the same random number. What happens there, we'll discuss later. That's a more advanced use case. But let's for now assume that they all pick different random numbers. Mr. Smith picked number 2, Amy picked 4, Bob picked 3, and Chris picked 1, and this is completely random, and Dora picked 5. Okay. So now what happens? Let's see what happens. Now initially the medium is busy. Let's assume that they're all sensing the medium, because they all picked a number, but they're all trying to sense the medium. So anytime you have information to send, you'll sense the medium, meaning you'll check if there is energy on the air. If there is energy on the air, you will not count down. You will keep your, what we call as your counter, right? Your backoff counter, because you're backing off from the number you're starting. That's why it's called a backoff counter. So you use something called as a backoff counter, which is a random number that is created within a range of numbers, right? So they all picked up a backoff counter, and they are not moving the counter. They all kept it at the same because they're seeing the medium as busy. Okay. So in the next instance, next time, they saw the medium free. So let's say the medium is free. No one is transmitting at the time. So then all of them will count down their Backoff counter. So Mr. Smith will count down from 2 to 1, Amy will count down from 4 to 3, and Bob would count down from 3 to 2, and Chris, who is the lucky guy, who seemed to have picked a smaller number, will count down to 0. And then Dora is the most unlucky person here. She is still at 5, so she's counted down to 4. Okay. So then in the next instance, again, you're sensing the channel, right? Now, if you're still seeing the channel free at this point in time, then now Chris can transmit. So when can Chris transmit, or when can anyone transmit? When they see the medium free plus their Backoff counter has gone to 0. Okay, both of them have to happen. If both of them happen, then that person gets to transmit. So now Chris is the only one who meets the criteria. At this time instant where you see this line here, at this time instant the medium was free and Chris's counter has gone down to 0. So Chris will transmit a 1 data frame, right? He'll send C1, right? And others will freeze their counters because they're seeing the medium busy. For everyone else, the medium is busy. So because for everyone else the medium is busy, they will actually freeze their counters, right? And then it will continue. And for the next session, once the medium is free again, this time Mr. Smith's Backoff counter goes to, they're all starting counting down again. So Mr. Smith went from 1 to 0. So now he gets to 0, but everyone else is, Amy is at from 3 to 2 and Bob is from 2 to 1 and so on, right? And then the next cycle, because again, both the criteria are met, the medium was free and the Backoff counter went to 0. Now it is Mr. Smith's turn to transmit. And he gets to transmit and everyone else will freeze their Backoff counters, right? Because the medium is busy again. So the requirement is anytime the medium is busy, you have to freeze your counters. Anytime the medium is available, you cannot transmit, you still have to count down. And when the medium is free and you have counted down to 0, then you get to transmit. So the next instance, again, there is countdown to 0. This time, Bob has went to 0, so Bob can transmit now, right? And so this way, what you have done is, there is no centralized control. There is no one person scheduling. But somehow, in a distributed fashion, they are all making sure that they are sending data and they are not colliding with each other. And there is some form of fair access. Now here it is not completely fair in this example because it's a little bit unfair to Dora because she picked a larger random number when compared to others. But statistically speaking, if you have done this over many times, then it is most likely that everyone will get equal access to the medium. Because remember that when this guy went to 0, see, for example, Chris was the first guy to transmit, he went to 0. After he transmitted, now he picked another Backoff number again and he went into the queue again. So now he's at 4. Now he needs to count down again, right? So anytime you get to transmit one frame, you are done, and then you pick up again a Backoff counter and then you back off, you get into the queue again. So this way, in a distributed fashion, you're trying to create a model where everyone gets fair access to the medium over enough sample set and no one collides with each other, right? Which is the beauty of how the distributed coordination function actually works. Now, of course, we might ask what happens if 2 people pick the same random number, which is very much possible. And yes, in that case, there will be a collision. Most likely there will be a collision. And if there is a collision, then they follow something called as a random Backoff or an exponential Backoff mechanism, where now they're saying, okay, well, there are 2 people who pick the same random number, and so they're colliding. So next time what they will do is, instead of picking a random number between 0 and 5, they will pick a random number between 0 and 10. So now they're doing something called as an exponential Backoff, right? So now when you are picking random numbers between 0 and 10, the probability of 2 people picking up the same random number is lesser when compared to picking up 2 people picking the same random number between 0 and 5, because you have a larger numbers to pick from, right? Sample set to pick from. So the probability of 2 people picking up the same random number actually decreases. So anytime there is a collision, you go off on what we call as an exponential Backoff. And we'll explain these concepts in a little bit more detail in the coming section. So hope this example makes sense to you all. And this is fundamentally how the distribution coordination function works. Now let us look at revise some terminology in this case. Right? So there are different terms that are used in this concepts. The one is clear channel assessment. We talked about this already. So this is where basically the radio is actually assessing the channel, right? As a part of CSMA. So then in the part of clear channel assessment, we already talked about this in one of the previous sessions. There are two things here. There is the signal detect and there is the energy detect, right? Signal detect is where basically you are able to detect some other signal, some other valid .11 frame, right? When you're able to detect that some other valid .11 frame, then you know that someone else is transmitting. Then you decide that the medium is busy, right? This is how you decide that the medium is busy. The other metric is the energy detect, where you're detecting some energy, which is, you can consider it as interference from other devices, right? In which case you have to back off also. So CCA looks at these methods. So if you look at this flow chart, if a device has frame to transmit, it will go off on the random backoff. So as I said, every device that has frames to transmit needs to do a random backoff, right? For collision avoidance. As it does the random backoff, it still keeps checking the channel at regular intervals. And if you see signal in the channel, that means that the medium is busy, then it will go back to the random, freeze its backoff counter and go back. But if the medium is idle, then it will check for energy. And if the energy is also not there, and which means that there is no interference, then it can become transmitting once the random backoff counter goes to 0. This is the CCA part, right? Now let's look at another term which is also very important, and this is called as the network allocation vector, or NAV, right? This is a very common term. In very, very simple terms, a NAV is nothing but a device basically taking a nap based on something that's happening on the network. Again, if you take this example, let's say Mr. Smith is the access point, and he says, "Hi everyone, I'll be talking to Amy for the next 30 seconds. So I need the medium," right? And when Mr. Smith says that, Bob, who's also able to hear Mr. Smith, will say, "Okay, I need to just chill for the next 30 seconds because I know even if I'm trying to access the medium, I will find energy on the air," right? So remember that most of these radios are in mobile devices, and in mobile devices we need to conserve battery power. So anytime the radio is sensing the medium, it is using up energy. And especially when you don't have to do that, you should not do it. So for example, when Mr. Smith is saying, "I need the medium for the next 30 seconds to talk to Amy," Bob should realize that even if I try to sense the medium for the next 30 seconds, I will see some energy on the air. So I need to back off, right? So I would rather not even check. Let me just turn off my radio and set an alarm for 30 seconds and wake up after 30 seconds. So Bob will just turn off his radio, set an alarm and says, "Wake me up after 30 seconds," and then he'll wake up again, and then he'll sense the channel again, right? So that is what is called as a network allocation vector, where you don't sense the medium or a channel for a certain amount of time based on the reservation that was done by someone else, right? This is something that is important to understand. Then there is the concept of interframe spaces. It's again a very important concept in Wi-Fi. Interframe space, in very basic terms, is just the space between frames. So if you're sending a data frame and then you send the next data frame, you have space between them. Just like when I'm speaking, I'm trying to create some gap between every word or every sentence that I'm speaking, right? And at the receiver, interframe space is already also very useful because the receiver needs to process. Like when I'm speaking, if I speak a sentence and then I pause for a little bit and then I say the next sentence, then that gives you enough time to process what I'm trying to say, right? So you need gaps between words and sentences for the receiver to be able to process that information. So that is the basic use of an interframe space, is to actually create gaps between sets of information so that the receiver can process it easily. But in Wi-Fi, interframe spaces are used in a very intelligent way, right? They are also used to create priority access to the medium in a very interesting fashion, which we'll explain that in the next few slides. For now, all I want you to know is that there are different types of interframe spaces, and they're of different lengths in time, right? The shortest one is the SIFS, or the short interframe space, which is can be like 10 microseconds or 16 microseconds, or in that range based on what kind of protocol you're using. And then larger than that is the PCF interframe space, or PIFs, and even longer than that is the DIFs, and even longer than that is the EIFS interframe spaces. These are interframe spaces of different time durations, right? And why do we need interframe spaces of different time durations? That is how you get priority access to the medium, by using the interframe spaces. So let me explain it using a simple example. Again, coming back to our favorite classroom example. This time, forget the random backoff thing I was talking about. Keep that for the side for a second. Let's say we're not doing any random backoff. Let us say we want to create some preferential access based on this concept of interframe spaces. So let us assume that Mr. Smith is the most important person because he's the teacher, and he picks a interframe space of 1 second, which is a shorter interframe space. And Amy picks 2 seconds, and Bob 3 seconds, Chris 4, and Dora 5 seconds interframe spaces, right? So now what happens? Now remember that they all have information to send, right? They all have information to send at the same time. And at this time instant, when at time 0, all of them are seeing the medium free at the same time, right? Everyone sees the medium to be free at the same time. But now what we are saying is there is a rule. The rule is that you have to see them. Not only you should see the medium, check the medium is free, but you need to make sure that the medium is free for the interframe space time, and that is the rule. So rule we are setting here is all these 5 people have to be seeing the medium free for at least the interframe space time before they can transmit, which means that Mr. Smith has to see the medium free for at least 1 second. Amy has to see the medium free for at least 2 seconds. Bob has to see the medium free for at least 3 seconds, and so on, right? Otherwise, they cannot transmit. So only if the medium is free for 2 seconds continuously, then only Amy can transmit. So that is the rule. Let's say that's the rule, right? So now that gives you priority access. Since Mr. Smith has to only wait for 1 second, after he waits 1 second, he still sees the medium free because no one else is transmitting, and he starts transmitting, right? But Amy is still seeing, has to wait at least 2 seconds. So Amy cannot transmit. Amy has to wait, because the moment Mr. Smith starts transmitting, Amy has to get into busy mode again, right? And then next time again, the medium becomes open here at this point after Mr. Smith has transmitted. Now again, everyone is checking the medium to be free. Now again, the rule is that Mr. Smith has to wait for only 1 second, and Amy has to wait for 2 seconds. So again, Mr. Smith will only wait 1 second. Again, he'll get preferential access, and he'll send his other frame. And again, Amy has to wait, right? Now, after Mr. Smith has finished all his transmissions, then Amy gets preferential access because she has to wait only 2 seconds for the medium to be free, when all these other people have to wait longer time, right? And this is how you create preferential access for any transmitter by using different interframe spaces, right? If the interframe is shorter, which means that you have to see the medium free for only a shorter amount of time, which means that statistically you get free, it's not deterministic. I'll explain why it is not deterministic, but for now assume it is deterministic, right? For simplicity purposes, you get preferential access, right? And that is the concept of interframe spaces, and this is how you use interframe spaces to create priority on the link. And then there is this other term called contention window, right? This is another thing that we'll normally hear. So contention window is nothing but, remember we explained that random backoff where you go from 0 to 5 or 0 to 10. So there is a window of numbers from which you can pick, and that is what's called as the contention window. So if you pick a number between 0 and 5, then your contention window length is about 5. If you pick a number between 0 and 20, then your contention window can be bigger, right? The bigger the contention window, the lesser the probability of any two devices picking the same random number. But again, the more the overhead, because you have to pick a larger number. That means you have to back off, you count down for longer time, which means you have to wait longer time, and which means that you get slower access to the medium. So a few terms to remember here are again basically CCA, and then there is network allocation vector, which is basically the time in which the receiver has to turn off, and the interframe space, we talk about interframe space, and then there is the concept of contention window. These are the kind of the four main things we need to learn in this area. Now let us apply all of that to this example of the Backoff algorithm, how Backoff algorithm works. So we were talking about Amy and all the classroom. Now I'm showing an example of real Wi-Fi. So if let's say you have these 5 devices, they're all trying to access the medium. And the very first instance, A already won the medium, and so he's transmitting data. and then he waits for an acknowledgement. He gets an acknowledgement. While that is happening, everyone else is setting their network allocation vector. They're all waiting, right? They're not transmitting. Now let's assume that at this time instant, they all see the medium to be free, right? They all see the medium to be free at this time instant. Now the rule says that everyone has to wait at least a diffs period or a distributed coordination function interframe space period, and then they need to start counting down their Backoff counters. So in this particular case, randomly A has picked a contention window of number of 9, B has picked 13, C has picked 4, D has picked 18, and E has picked 26, right? So they all start counting down. So by the time they count down 4 numbers, C has gone down to 0, right? And so he gets access to the medium and he transmits. And then when he is transmitting, everyone else is setting their nav or the network allocation vector, because they're freezing their Backoff timer. They're not counting down anymore, right? And then again, once the medium becomes available, they all wait for a diffs period, and then they all start counting down again, right? So they start counting down. And remember that by this time we counted on 4 here. So this guy is not 9 anymore, he's 5. And this guy is not 13 anymore, he's 9. So they're all counting down. So now we start counting down again. And it so happens that this will go to, after 5 numbers, he will go to 0 first, right? And so he transmits, A transmits. And then others are again freezing their Backoff counter. So this way, what happens is every device will pick a random number, they'll start counting down. And then whenever it's their chance to transmit, they will transmit. And once a device successfully transmits, it has to pick a new random number again. So it gets back into the queue. So statistically speaking, there is a state, like, so for example, let's say there is D or E. They didn't get to transmit. He picked a very large number, 26. But over a period of time, after 2 or 3 transmissions, his counter will eventually go to 0, right? And then he gets to transmit. So over a period of time, statistically speaking, because there is this concept of contention window, everyone will get a chance to transmit. It might be, one might be a little bit ahead of the other, but next time there is a probable chance that he would pick a smaller random number. Instead of 26, he might pick only 2. So statistically speaking, over enough number of samples, it will all even out, and everyone gets equal access to the medium, while no one is colliding with each other. So that is the beauty of the distributed coordination function collision avoidance mechanism. So hope that made sense, right? Now there is this concept of data transmission. So so let's say the client is sending a data frame to the access point, and the access point is sending an acknowledgement. Okay. Now there are certain communications within Wi-Fi that need to be continuous, and in other words, they have to be atomic, right? So for example, if a transmitter or a client sends a data frame to the access point, now the data frame has been sent, which means that after the transmission is completed, the medium is now free. Okay, everyone sees the medium free because the data transmission has completed. Now we need to somehow make sure that when the medium is free, only the AP should get access to the medium, because the ACK needs to come back right after the data frame. So when the client 1 is sending a data frame to an AP, and after the transmission is completed, if someone else sends some other data frame, now the medium is busy. So the AP cannot send an ACK. If the AP cannot send an ACK, then the client will assume that the AP did not get the frame. And so that will time out, and the client has to now retransmit its frame. We don't want that, because that is a waste of medium time, right? So what we need to do, we need to ensure that anytime a client sends a data packet to an AP, or a transmitter sends a data packet to receiver, only the receiver should get access to the medium to send the acknowledgement. No one else should get access to the medium. So how do you ensure that? You ensure that by saying that the AP has to wait only a SIFS time, or a short interframe space time, to send the acknowledgement, and every other transmission has to wait at least a diffs time. So a SIFS could be 10 microseconds, a diffs is, let's say, 50 microseconds. Okay, so this is how you ensure that only the ACK will follow after the data frame, and no one else gets. At this point in time, if multiple devices see the medium free, then the AP has to wait only a SIFS time, and it can send the ACK, and everyone else has to wait at least a diffs time before they can send the next frame. And this is how you ensure that the data ACK combination is atomic, and there is no one else getting in between. So this is why I'm saying interframe spaces are very useful for creating preferential access to the medium, right? And that is how the data transmission will happen. So anytime you have a high priority frame, let's say you want to send an RTS frame or a CTS frame or a beacon frame at regular intervals, and that is a higher priority frame, then those frames have to wait for shorter interframe spaces and not longer ones, right? So that way they get preferential access to the medium. And there are multiple people accessing the medium at the same time. We want one person to get preferential access based on the importance of the content. So in other words, after the data frame was sent, the most important frame in the entire wireless LAN cell is the acknowledgement. Nothing is more important than that. So which means that you say, okay, acknowledgement, you only have to wait a SIFs, and everyone else to wait at least a diffs. And so it makes you gives you higher priority. So that's an example of how this interframe space works. Now the concept of exponential backoff. What happens when there is a collision? As I was mentioning before, anytime there is a collision, there is this concept of exponential backoff, where now the transmitter assumes that the medium is quite busy because of that I'm seeing collisions. So let me wait a little longer. So it actually uses something called as an exponential backoff mechanism, where it picks slots from a higher number of slot count. So initially, let's say your contention window size is 31 slots. Then if you exponentially back off on your first retransmission, you will pick between a random number between 0 and 63. You basically exponentially increase your backoff order. If you still lose the frame in the second retransmission, now you pick a random number between 0 and 127, right? And so basically what you're saying is you're slowing down your transmission. You're reducing the probability of error every time a frame is lost. And this is the reason why retransmissions are very costly. The retransmission is very costly for two reasons. First, you are retransmitting the same frame, which means that you're wasting the airtime because you're sending the same information again. And second, anytime you're retransmitting, you have to wait much longer because you're exponentially backing off. So that adds even more time delay, right, when you have retransmission. This is one of the reasons why retransmissions can increase the latency, right, for the end user, because every time you're doing a retransmission, you're resending the same information, plus you're waiting much longer to send the same information, and that increases the latency substantially. So this is the reason why you want to avoid retransmissions as much as possible. Now, if you apply the same concept to what we call as the WMM QoS, right? Now, remember that I was talking about different interframe spaces. How do you make sure QoS works? This is a very interesting concept. QoS, again, in Wi-Fi works in a way, what we call as a very distributed fashion, right? So, for example, let's say these are two devices. Let's say this guy has voice traffic to send, high priority traffic, and this guy has best effort data traffic to send. Both of them have packets to send, and both of them are seeing the medium at the same time. So to implement QoS, what the standard says is the person who has higher priority can use a shorter interframe space to access the medium, and it's called AIFS, or arbitrary interframe space, right? And the guy who has lower priority traffic needs to use a longer interframe space. So which means that when both of them see the medium free at the same time, the probability of this person getting access to the medium is higher because he has to wait only lesser amount of time, and he has to wait longer amount of time when he sees the medium free. So that is one way you can create QoS, right, in a distributed fashion. The other factor is the contention window size. So when you're doing this random back off, what we can say is for the higher priority traffic, you pick a random number from a smaller range, a smaller contention window, right? And for lower priority traffic, you pick a random number from a larger contention window, right? Remember the example of Amy and all the students we're talking about, where Dora picked a random number 5. That happened randomly. But what if Dora had to pick a number between 0 and 50, and Amy has to pick a random number only between 0 and 10? So now Amy has a higher probability of getting the access to the medium because it might have picked a number 5, and Dora might have picked 45, right? Because it has picked between a range of 0 and 50. So by doing that, you are creating preferential access, or what we call as a better access to the medium, which results in better quality of service. So in Wi-Fi, there is this concept of WMM, where you have these access categories. We call them access categories. So different categories to access the medium. So that's why it's called access category. And we call them best effort, background, voice, and video. There are 4 access categories. And when you're trying to access the medium, you give different AFS values or arbitrary interframe space values represented in this number of slots here. And then you also give different Backoff counter ranges, right, for each device. So what you're saying is if your traffic is voice, right, voice traffic, your AF is only 2 slots. You only have to wait 2 slots. And your Backoff counter contention window is only between 0 and 3. So you pick a random number between 0 and 3. But on the other hand, if your background traffic, which is the lowest priority traffic, your AFS value, which means that the amount of time you need to make sure the medium is free, is 7 slots, right? And then your random Backoff number is between 0 and 15. So now you're like the most unfortunate person, because not only you have to see the medium free for a longer amount of time, but you even have to back off for a longer amount of time. So which means that you get lower priority. That does not mean this guy is going to starve completely. His performance is not going to be 0. That is the beauty of this protocol. Over a period of time, he eventually gets to transmit. So let's assume that all 4 queues, all 4 priorities have a lot of traffic to send. It is still statistically possible that this guy will get some traffic through, even though he is a little bit unfortunate when it comes to the is a bit of a disadvantage when it comes to the access of the medium, right? And that is how the WMMQoS protocol works. So in the interest of time, I'm not going to go into all the details, but one point to remember is there are different queues, and the way you provide preferential access in a distributed fashion is by picking different AFSN values and also different contention window values for each access category when you transmit the frames. So that's how the QoS algorithm actually works. Now, how does the AP implement it, right? And there is something called as a EDCA parameter set inside the access points beacon frame. So when the AP is sending out beacons, inside the beacon, the AP has this information element called the EDCA parameter set. Inside the EDCA parameter set, it will tell the entire cell, if you're having best effort traffic, you use this AFS value and you use this contention window size. If you have voice traffic, you use this contention window size and this AFS value. And that information is broadcast to all the devices, which means that any device that has a certain type of traffic will use those parameters for accessing the medium, right? And by controlling those parameters a little bit, you can actually control the degree of QoS. So for example, if you set a very large contention window size and very large AFSN value for the background traffic, and very small contention window size and very small Backoff values for voice traffic, then you are creating a huge gap in quality of service between the voice traffic and background traffic. If you bring the numbers closer, then there is a little bit closer to each other. So you can control to what degree of quality of service or what degree of priority you can have by controlling these EDCA parameters inside the beacon, and that can be controlled by the AP. Some of the APs will actually allow you to set those parameters also inside the access point. So if you look at the example here, if you look inside a beacon, so this is a beacon frame. If you look at inside the beacon, there is something called as a EDCA parameter set here. So you see inside the EDCA parameter set, for each access category, best effort, background, voice, and video and voice, there is this AFSN values, and there is also the contention window size. These are in hex codes. Of course, you can convert that into decimal values to see what those values are. But this is what the stations have to follow. They have to follow these parameters when they're transmitting traffic with QoS. So that is how this works. So now I wanted to show you a quick demo or a simple example of how this QoS works. So what I have is here a small demo where I'm using a Wi-Fi router in our lab here, and there is a traffic generator on the wired network that is representing the internet, and this traffic generator source is actually sending different types of traffic, right? And the Wi-Fi router is now there are 4 different Wi-Fi clients connected using basically our client emulator box. They're all created in the same box, and so we have created 4 Wi-Fi clients, and now we're sending one traffic stream to each client with different priorities. So for example, we are sending this is the background client, best effort client, video client, and voice client, and to each one of these clients, there's one traffic stream. On the wired side, we are creating the equal amount of load on all 4 streams, and the combined total of the load is more than the medium capacity. One thing to note in QoS is QoS doesn't make sense unless you overdrive the channel. If you have enough access to the medium, if you have enough bandwidth, then QoS is never needed, actually, right? This is, in fact, that's how they've solved the QoS problem in Wi-Fi. In many ways, for many generations of Wi-Fi, QoS has not been used very well, because normally what they have done is anytime QoS became a problem, they just threw more bandwidth at it, right? It's just like how the roads work. Let's say you have roads and you have congestion on the roads, right? Rather than implementing better ways to admit traffic into the onto the roads, and rather than making better street lights, traffic light system, they say, okay, let's add more roads. We'll add 2 more lanes, 3 more lanes, 4 more lanes, and that's how we solve the problem. That's how Wi-Fi has traditionally solved the problem of QoS, by throwing more bandwidth so that QoS doesn't become a problem. So the one point to remember is QoS is really a problem when there is a bandwidth constraint. So that's the reason why, to test QoS, what we are saying is, let us overdrive the system beyond its medium capacity. So when we overdrive the system, then we can see QoS in action, right? And so let me show that quick demo here. I go to my system here and VNC into it. Here, what I've done here is I created 4 Wi-Fi clients. They're connected to the access point, and inside the access point here, this is a Netgear access point I have. In this access point, I've already enabled QoS. If I go to the basic settings, there should be settings somewhere which shows QoS. So I've enabled QoS. Looks like I logged out here, but I enabled QoS inside the user interface. So now what I've done is, on this access point, I've created 4 virtual clients. One of them is best effort, another is background, one is video, another one is voice. And then I created the 4 traffic streams. So there is a voice traffic stream sending voice traffic to the voice station, video traffic to the video station. So how do you know it's the voice traffic? So if you double click and look at the details of the traffic stream, I set the priority to voice. So you have all these priorities. So since I'm sending these packets from the Ethernet side, I am setting the IP toss value, because in the IP header, right? This is not Wi-Fi. I'm sending it from the Ethernet side, and at IP packet level, at the network layer level, I'm setting the IP toss bits. And so what the AP will do is, it will receive those packets, and then it will map them to WMM user priorities, and it will apply QoS when it transmits the frames on the air. So if you look at this example here, because we have preferential access set here, the AP will be using a smaller interframe space and a smaller contention window size for these packets, and so it's able to send more, and here is able to send less, and here is able to send less, and here is able to send even lesser, right? And that's how the QoS works. So now if you see that in action here, I'm starting. So for example, for the voice traffic stream, I set the voice category. For let's say best effort, I set the best effort category, and I'm trying to send 1 gigabit per second traffic to each one of these traffic flows, which is above the medium capacity. I'm using, I think, 11 AC 2x2 MIMO, so which is above the medium capacity. So now let's say if I select all these traffic streams and I start them, you'll start seeing here that this is the number of packets per second that were sent. So the voice category is able to send around 9,000. It's already at 10,000 packets, but video was able to send 7,000 packets, and then the best effort is only able to send 600 and something, and then background is set to 0, which is not how it should be. Actually, this is not a very well functioning AP, because as I mentioned, statistically speaking, none of these access categories should completely starve. Everyone should be able to send something, but they'll be able to send different amounts. So now you can see it send 1 packet right here. And so, but you can see clearly voice traffic is getting much higher priority when compared to video, when compared to best effort, and when compared to background, right? And QoS is clearly working. Now, if you go to the AP and if you turn off QoS and you run the same test again, then you will most likely see equal number of packets being sent on all 4 traffic streams, right? So this is just a quick demo of how QoS and how all the concepts that I talked about are in action here. The concept of interframe space in the term in the form of arbitrary interframe space, the concept of contention window size, the concept of NAV, network allocation vector, the concept of random backoff, the concept of exponential backoff. All the things that I mentioned, they're all in action to make this particular thing happen this way, right? In this priority, which is quite fascinating. So that is a quick session. Unfortunately, it's a little bit of a complicated concept to explain, especially to people who are new to this. So hopefully this made some sense. Here are some references where if you want to go and study more about these sections, about these concepts. That's all we have for this session. Just to quickly summarize, we talked about medium access and random backoff, and we talked about contention-based mechanisms. We talked about interframe spaces and all these other fun concepts. And we also talked about WMM or QoS. So that's it for this session. And over to any questions.